Most quantitative equilibrium problems can be made easier to solve with the use of proper visual representation. What's described in a sentence can be difficult to determine what to do with it. But once the given information is rewritten in a logical and visually more recognizable form, you can more easily make the connection between what is given and what is asked. The tool we are going to use is called I.C.E tables, I.C.E standing for initial, change, and equilibrium. Underneath the reaction equation, a table is made to show the initial, change, and equilibrium amounts for each reactant and product. Then the given information is placed in its appropriate box. For our question here, 1 mole of phosphorus pentachloride is placed in a 1 liter container, and it is allowed to come to equilibrium. That means the reactant is placed, and once equilibrium is reached, we got all 3 species, the reactant and the 2 products, in equilibrium. At that state, the mixture is found to contain 0.135 moles of phosphorus trichloride. So this is the given information which we are going to plug into the I.C.E table. The number of moles of phosphorus pentachloride is given, the initial state. There is no mention of anything else. That means the amounts of the products are 0. And at equilibrium, it is found to contain 0.135 moles of phosphorus trichloride. So far, we only transcribed the given information into the I.C.E table. We haven't discovered or calculated anything new. Once the given quantities or concentrations are put into the table, the empty cells can be calculated. The table is constructed in a way that initial plus change is equal to the equilibrium value. The sum of the first 2 boxes is equal to the third box. Looking at the given information we have placed already into the table, it is clear that we can determine only the change in phosphorus trichloride amount. There isn't enough information to do any other calculation. So if the amount went from 0 to 0.135, the change must be 0.135 moles. It's a positive change because it's increasing. Once the change in phosphorus trichloride is determined, we can calculate the change in other species. Let's first calculate the change in the number of moles of chlorine. We're going to use the stoichiometric ratios, 1-to-1 ratio, to convert the moles of phosphorus trichloride to moles of chlorine. It also calculates to be 0.135 moles. Because the reaction is proceeding to the right to make more of the products, chlorine change is also a positive change. It must increase. You cannot decrease from 0. You cannot have a negative quantity. Therefore, the equilibrium quantity of chlorine will be 0 plus 0.135 moles to be 0.135 moles. How about the change in phosphorus pentachloride? We can do the same stoichiometric calculation, but this time converting the moles of phosphorus trichloride to the moles of phosphorus pentachloride. The mole ratio is again 1-to-1 because the coefficients are 1 and 1. This gives us the change to be negative 0.135 moles. The quantity is 0.135 calculated through stoichiometry, but the sign is negative because the change is negative because the amount is decreasing as this reactant is consumed in the forward reaction. Therefore, the equilibrium amount is going to be 1 minus 0.135, which is 0.865 moles. Because the question was asking the molar composition of the equilibrium mixture, the quantities in moles in the equilibrium line is the answer to the question. Let's see another example of the application of the I.C.E table to solve an equilibrium problem. In this question, 0.7 moles of sulfur dioxide and 0.7 moles of oxygen are placed in a 3-liter reactor and are allowed to reach equilibrium. At equilibrium, the reaction mixture was found to contain 0.5 moles of oxygen, and the question is to calculate the value of the equilibrium constant. We need to first construct an I.C.E table. And then into that I.C.E table, we're going to put in the given values. We're given the quantity of sulfur dioxide, 0.7 moles, and the quantity of oxygen, also 0.7 moles. There is no mention of sulfur trioxide, therefore its starting amount is 0. And lastly, we're given the quantity of oxygen, which is measured at equilibrium. Therefore, 0.5 moles of oxygen will go to the equilibrium box. Next, we are going to calculate the empty boxes. Once the quantities or concentrations in the given question are placed into the I.C.E table, the rest is to determine the quantities in the empty boxes. Our starting point will be oxygen because we know 2 of those boxes. That means we can find the change. To go from 0.7 to 0.5 moles, the amount of oxygen decreases by 0.2 moles. Because it's a decrease, we have to show it with a negative sign. Now we know the change in oxygen, we can calculate the change in sulfur dioxide. Now pay attention to the stoichiometric ratios. For every 1 mole of oxygen reacting, 2 moles of sulfur dioxide reacts. Therefore, twice as much sulfur dioxide should be consumed. Therefore, the change in sulfur dioxide is 0.04 moles, and a negative because it's decreasing. Therefore, the equilibrium amount of sulfur dioxide is 0.3 moles. Similarly, the ratio between oxygen and sulfur trioxide is 1 to 2. If 0.2 moles of oxygen is being consumed, then 0.4 moles of sulfur trioxide must be produced. It's produced because sulfur trioxide is on the product side. The reaction is moving from left to right. Therefore, the reactants are decreasing, the product is increasing. Therefore, the positive sign. Therefore, the equilibrium amount of sulfur trioxide is positive 0.4 moles. Now it's time to calculate Kc. This is the Kc expression written using the balanced chemical equation. This expression requires the concentrations in molarity to be plugged in. Therefore, our next step will be to calculate the molar concentrations of each species. The number of moles of each is in the equilibrium line, and the volume of the container is given in the question. For sulfur trioxide, 0.4 moles divided by 3 liters gives you its molarity. You repeat the calculation for sulfur dioxide using its number of moles and the given volume, and also for oxygen. And then you plug these values into the Kc expression and eventually calculate the value of the equilibrium constant as 10.6. Remember, Kc has no units. Now it is your turn to apply your understanding of the equilibrium concept and the use of I.C.E tables to this problem.